All right, so moving on to LPM. What is LPM? It is a modified wide gap brazing repair process that was developed and patented by Liburdi Turbine Services. LTS has an over 30-year track record with LPM and have repaired thousands of component sets using the repair technology. We've used it extensively on industrial components, both heavy duty industrial and aeroderivative components. And it's also an FAA approved process that's used for aircraft component repairs. What are the advantages of LPM in comparison to other repair technologies? So in comparison to welding, which is a commonly used repair technique for turbine components, LPM offers both improved strength over commonly used weld fillers, and it also eliminates or significantly reduces the cracking or distortion that occurs with welding. And so with welding, those are issues that are commonly encountered, and so that limits the size and the surface area that we can repair on components. Whereas with brazing and LPM specifically, it's a process that allows us to repair much larger surface areas, much larger crack sizes and defect sizes because it avoids the cracking and distortion associated with welding. In comparison to other wide gap brazing processes, the big advantage of LPM is that it allows us to do much larger gap sizes, so up to 10 times larger gap sizes. Material restoration is possible with LPM up to a ½ inch gap size, whereas with conventional wide gap braze repairs, they're generally limited to between 4 and 40 thousandths of an inch. And we see at the bottom of the screen an example of a part that has had LPM applied to it and repaired. So those are kind of the purple stripes you see on the part there. And then we see that same part that's gone through another full service interval, and we see the repair materials held up well during service and is free of cracking, even in the areas that had cracked during the prior service and required repair. So getting a little bit into the technical side of how the process works and why it offers these advantages over other repair processes. As mentioned, LPM is a modified wide gap brazing repair process. A braze is an alloy that has a lower melting temperature than the material it is being used to join or repair. So in contrast to welding, when we're welding, we're melting both the repair filler material as well as locally melting the part itself where the repair material is being applied. With brazing, we're only going to a temperature where the filler material or the braze alloy melts, but the part itself that is being applied to does not melt. For nickel and cobalt alloys, brazes are typically composed of nickel or cobalt alloys. They contain generally chromium and may contain other alloying elements, but in particular, there's generally boron and or silicon that are added to these alloys in order to lower the melting point. So as previously stated, we need an alloy that has a lower melting point. The way that's achieved in nickel and cobalt alloys is by adding boron or silicon, which are termed melting point depressants. So the addition of these elements is useful in that it allows us to create braze alloys with lower melting points, but they also are detrimental, and so we want to only add as little of these melting point depressants as possible. So with our LPM process, we have a part that comes out of service and we have damage on our component. So we see an example at the left center of our slide here. We've got an example of a crack or some damage on the surface of a component. With our LPM process, we go in and mechanically remove that damage. So we'll use tools or machining to remove the damage. And then, as stated, we apply our LPM materials as shown at the second from the left in the center. So the LPM materials can be applied in two forms, either a putty or a tape. The putty is generally used for where we have irregular shapes, such as cracks, or example, we've removed a crack and we have a groove, and then we can use our putty to fill that groove that's been created. Or in contrast, where we want to do uniform buildups of thickness on a wall, we can use tapes. Our first layer is the high melt constituent, which has a composition and melting point similar to the part that's being repaired. We then apply the braze constituent on top of that in a fixed ratio. The part then goes through a heat treatment, and after going through a heat treatment, we end up with solid metal where our repair materials were applied, and then we machine or blend the part back to the original contour. Looking at a more microscopic level of what's happening during the heat treatment process, we see at the bottom an example of what's happening with our powder particles. So we start with our high melt filler powder particles packed into our groove. We then go through, as we increase in temperature during our vacuum furnace heat treatment, we start getting ligaments or sintering happening between our high melt powder particles. We then heat treat to a temperature where our braze has melted, but the part and the high melt powder have not melted. And at this point, when our braze becomes liquid, it then flows into the spaces between our high melt powder particles and fills those voids between our high melt powder particles by capillary forces. We then go to an even higher temperature where we get consolidation and homogenization of our repair joint, and we get solid grains forming upon cooling. We're going to move on now to some examples of repairs that we do with our LPM process, starting with repair of the PW2000 stage 3 vane. This is an FAA approved repair that we do. The parts experience hot corrosion damage during service, which you see at top left in the seal slots on the sides of the components. We go in and we mechanically remove all of that corrosion scale and damaged material and end up with a widened slot or groove. We then fill that whole slot and build up material on that side face with our LPM materials. You see at top center an example of a part that's had the LPM putty applied on that surface and has gone through the vacuum furnace heat treatment and been consolidated. And then we go through and do final machining and restore the geometry of the slot on the side of that component. And then it's ready after coating to go back into service again. We see at bottom an example of the microstructure in that slot. So we see at the bottom of the micrographs are Marm 247 base material. And then on top of that, we see the LPM material that's well bonded and has a dense microstructure to that part. And here we see the same component type after it's gone through a full service life. And so we see that the LPM material is held up extremely well in service, that it's got the same dimensions and shape as it had going in. And when we did a cut up, we see our LPM material is free of damage and looks effectively like it did prior to going into service.